Welcome to CEC lectures. Myself Dr. Preeti Jagwani from Department of Computer Science, Aryabhat College, University of Delhi. So in our present series of database management systems, in our previous lectures, if you remember, we have covered the topic of hashing and indexing, and why this indexing is required in order to we can say to have a faster access for our databases and its whatever information we have stored in databases. Now the question basically comes up, which we have already covered in indexing, is what actually indexing is, and that I have told you in a nutshell just right now, and what type of indices. So we have seen ordered indices, or also hash indices we have seen, and within the ordered indices we have seen the dense index and sparse index also, along with the examples and figures that we have seen. So, from continuing from that particular index topic, today's topic is about multi-level indices. Now, when we talk about the term index, what is the basic agenda? Why why do we want to have an index? And that's the fact which we have established in our previous lectures also, that the only agenda which is it is to search in a fast manner, or we can say we want to access the information in a speedy manner, in a fast manner, and we want the information quick. Now, what is happening here? Let us consider a dense index on a particular relation, and that relation is, let us say, having 10 lakh tuples, and with the setups, with the big data things which we are talking about nowadays, having 10 lakh tuples in a relation is, I am sure, is perfectly a possible scenario in a real life application. Now, total 10 lakh tuples in a relation, so obviously your index entries are going to be smaller than the data records, and here a disclaimer here is we are assuming, or we are talking about a dense index. Now, let us say we are looking for, we are looking into these index entries more closely, and assuming that 100 index entry is going to fit on a particular disk block. Now, which disk block I am talking about? The block, or a particular kind of an area on your hard disk, and this 100 index entries is going to take a 4 kilobyte, a 4 KB block. So, basically this index is going to occupy, let us say 10,000 blocks with that much of relations, that that's 10 lakh relations. So, if a relation instead is having more rows as in for example, we are talking about crores of tuples, the index would instead occupy itself 10 lakh blocks, or 4 gigabytes of space. So, 4 gigabytes of space, when we talk about just for the index, it is huge. I mean, this is what we are talking about, is of the index, not the space, or not the storage of the relation. We are talking about the storage which is being occupied from the index is occupying this. So, that 4 gigabytes of space is being occupied by the index. So, such large indices are stored in on the disk, and what kind of file we are talking about which is going to store these indices on the disk? These are sequential files. So, such large indices are stored on the sequential file on the disk. Now, you are well aware that of the fact that whenever we are talking about something which is available in the disk, and our processor or our CPU wants to access that, that data has to be brought into the random access memory, or we can say in our main memory. So, if an index is small enough to be kept entirely in the main memory, then obviously our life is easier, and the search time to find an entry is going to be very low, because everything is available in the random access memory at once. That means the index, the size of the index is small, so that it can be kept in the main memory in one chunk. For example, now another scenario is, let us say we are talking about these kind of indexes, for example, which are taking 4 GB of space. So, 4 GB of space, if one particular index is taking, and what if we are going to take that particular index and going to store that whole index into the random access memory. So first of all, the question is, can we do that? So yes, this is perfectly possible, although with the large size of random access memory which is available nowadays, we can say yes, this is a possible scenario that 4 gigabytes of space of random access memory is available to a index. But before giving this verdict, we also need to see that there are other things, there are other items. For example, one of which is operating system. Your operating system has to be in the main memory, random access memory, then only your machine is able to work. So what I am trying to establish here is this 4 GB space. If let us say one memory is of 4 GB, or maybe let us say of 8 GB, which are very common figures nowadays. So index is so large that yes, it can be kept in the memory, but other items are to be kept in the memory also. Now the situation is, what if the index is large, so that it is not going to fit on the memory in one chunk. So that means these index blocks must be brought from the disk where as and when they require. So that means we need to have blocks of the index onto the disk, and these are to be fetched from the disk according to the requirement. And even if an index is smaller than the main memory of the computer, we have other things to be kept into the main memory, as I have told you, is operating system, and many other things which you have are definitely covered in general topics. So main memory is also required for other number of tasks. So even if you have a index is smaller, it may not be possible to keep that index entirely into the memory in one chunk. And another scenario, if your index is bigger enough, or index is kind of we can say is large, and it cannot be kept into the memory in one chunk, then in that situation it has to be brought. So what have we established here is, it is a perfectly possible scenario in both the cases, whether the index is small or whether the index is large, that it is not possible to keep the entire index into the memory. Now when it is not possible, the search for an entry in the index then requires several disk block reads. So for example, we are looking for an entry in the index, and then we are looking for that entry, and in order to search that entry, several disk block read operations are required. So what are we going to do in this scenario? Because reading a particular block from a disk, that is a kind of an, we can say kind of a disk operation, and these disk operations are relatively very slow as compared to reading from the random access memory. And because of the size of indexes, we cannot keep them all into random access memory at once. That means we are in a way bound to have those indexes into the disk, and our disk is something like that, that is costly to read. So there is a problem that our cost is increasing, and also obviously disk read is a slow operation. So the time is also kind of we can say increasing. So now there is a problem. The problem, if you can see, is kind of more of optimization problem. So in order to deal with this, we are going to treat the index, here I am talking about the large index obviously. So we are going to treat the index just as we would treat any other sequential file, and we are going to construct a sparse outer index on the original index. So what I am trying to say, we have a relation, then onto that relation we have a complete original index, and that is I am assuming is a dense index, and onto that index, or considering that index as the base or as the base file, we are going to construct one sparse outer index onto that particular uh, inner index, and your index entries are always in the sorted orders. so basically your outer index we can have in a sparse manner. Your inner index is definitely is going to be we can say a dense index because of the ease, or because of the speedy manner in which we can work with dense index as compared to the sparse one. And this fact we have already kind of seen in a quite detailed manner in our last lectures, when we explored both of the topics of dense index and of the we can say the sparse index both. So here we are having two indexes, one on the original file and another one on the index itself, and the outer index is actually an sparse index and the inner index is going to be a dense index. Now the question comes up that how it is going to help us in order to solve a problem of increasing cost, or maybe we can say increasing time, and what is required to in order to locate a block. So first of all, in order to understand it clearly, let us take a look at the figure which is given on the screen. And in this figure you can have you can see the three layers. So I am starting from the first layer, which is actually an outer index. That outer index, if you can see, is pointing towards an inner index, and each entry of the outer index is pointing towards one particular block, I can say, or one particular section inside the inner index. So that is why I am saying my outer index is an sparse index. Then coming to the middle level, which is of the inner index. So here the inner index is actually the dense index, which is pointing towards the original data blocks, and these original data blocks are nothing but we can say these are your original tuples or your original data which is stored in the relation. So here if you can see what is happening here, one level we have an outer index, obviously that is an sparse index. Then at the inner level we have a dense index, and that index, the dense one, the inner index, is actually being indexed or is actually being pointed with the help of the outer index or the sparse index, and then that particular inner index, which is the dense index, in turn at the final stage is pointing towards the various data blocks. Now what various data blocks is, you have the first pointer pointing towards the starting or the beginning of the data block 0, then you have your second pointer pointing towards data block 1, and then so on and so forth. So this will be the situation which I am talking about in case of and this type of facility is known as multi-level indices, because one index is the inner index, and on that inner index we have built one outer index also. So in all at we have two levels of indexes. So the name itself suggests as multi-level indices. Now after kind of understanding the way it is being organized, the way it is being arranged, what do we need to see? The indexes are there for in order to locate a record, in order to search a record. So even if we are kind of inserting a record, or even if we are deleting a record, the one common operation which we need to do is locating a particular record or searching a particular record. So what is the strategy when we want to search a record? We first use the binary search on the outer index in order to find the record for the largest search key value, which is less than or equals to the one which we desire. So basically in the outer index we are going to look for that which particular inner index block we are going to target in order to look for a. Now why I am saying we are looking for the largest search key value which is less than or equals to the one which we are looking for, or the one which we are desiring, because please remember your outer index is nothing but a sparse index, and this is the way we operate within the sparse index, that we look for the search key, or we look for the largest search key value which is less than or equals to the one which we are actually targeting. And this we have already seen in our previous lectures in details, along with the various examples, if you remember, that how to locate a particular record in a sparse index. And then after pointing, or after we can say getting that particular point, getting that particular pointer, the pointer points to the block of the inner index. So what we have done with the method of looking into the sparse index, or locating a record into the sparse index, we have taken the pointer, and now that pointer is taking us to the block of the inner index. Now in inner index we need to look for the actual pointer, which in turn will take us to the real or the actual data. But the inner index here is a dense index. So it is easier to we can say locating a particular record in a dense index, because each and every search key is already entered into the index, and for that what we need to do, we need to scan the block until we find the record that is having the largest search value less than or equals to the one that we are desiring. So here is a kind of we can say perfect possibility of getting the key value equals to the one which we are desiring, because our index is a dense index and each and every search key value is being entered over there. So either we are going to get the largest search key value which is less than, or we are going to get the original key value or the targeted key value, we can say. And whenever we are going to have the targeted key value, and then by following a particular pointer to the actual relation, we can say, we are going to jump upon the desired information which we have started with. So the pointer in this record points to the block of the file that contains the record which we are looking for. So first of all, what we did, we have taken the sparse index, which is the outer index, look for the particular block in the index on the inner index side, and by scanning the that particular dense index which is on the inner side, we are going to have a pointer which is going to point to the block of the file which is having the record which we are looking for. So now if given this figure on the screen, as we have seen that figure earlier also, and then I have explained the whole whole procedure of how to locate a particular data, you will be able to connect the dots. I can say that how we are jumping from one particular level to another particular level, and finally we are coming up onto the data which is desired. So from outer to then inner index, and from the inner index to the we can say our original data blocks by following the pointers. That's a kind of a simple choice. And these type of indices, as I have already told you, are having multiple levels. So one is having an inner level, another one is at the outer level. So we can say dealing with the multi-level indices. Now what is going to be the effect of having this multi-level indices? So an inner index, taking that the previous example of, let's say 1 crore tuples into the inner relation. So an inner index with 10,000 blocks would require 10,000 entries in the outer index, which are going to occupy just 100 blocks, because these these are we can say sparse indices. And if we assume that we are only keeping the outer index which is already there in the main memory, we would read only one block, we can say one index block for a search using a multi-level index, rather than 14 blocks which we were reading earlier along with the binary search, which is based on one particular level, which was not based on the multi-level indices. So, outer index when kept in memory, we are going to read one index block for a search using multi-level index, and as a result we can perform 14 times as many index searches per second, or we can say per unit time. So, basically our efficiency or our speed has been kind of we can say increased by 14 times. So, if our file is extremely large, even your outer index may grow too large to fit in memory. So, then what will we do? So, earlier we have taken an example when our index is going kind of we can say out of the memory, and then we have taken the two levels into it. Now, we are saying that our file is so large that even outer index is growing large to fit in memory. So, in that situation we can increase the levels. So, multi-level indices when I am talking about is just not like that you have two levels only. You can have multiple levels. We can create yet another level of index, and we can repeat this process as many times as necessary. So, let us say for a tuple relation, the figures which are given on the screen, let us say we have 1 crore of or maybe more than tuples in the relation. The inner index would occupy 10 lakh blocks, and the outer index will occupy 10,000 blocks, or we can say 40 megabytes. So, having a 40 megabyte index in our random access memory is perfectly okay, or it is 40 MB something in the memory is perfectly fine. Now, since there are many demands on this memory, it may not be possible to reserve that much of the memory which we were talking about earlier, let us say 4 GB or something of this, but this 40 MB seems sensible. But if your kind of data is growing many-fold in terms of we can say size, we can create yet another level of index, and we can also repeat this process as many times it is necessary. And indices with 2 or more levels, as I have told you, are multi-level indices. So, searching for a record in a multi-level index requires significantly fewer input output operation than doing a search for doing a search for a record in one layer of the index only, and that too even with a binary search, that is a costlier operation as compared to a multi-level indices. Now, if your index is not fitting into the memory, the access is going to become a little expensive. In order to treat that, we can say we will be keeping the index onto the disk as a sequential file and construct a sparse index onto it, which is the outer index, and then we have inner index onto the basic file, and indices at all levels. But one thing which is kind of a word of caution here is indices at all levels must be updated on insertion or deletion from the file. So, in this lecture we have covered the topic of multi-level indices and how it is going to give us the solution to the problem of a slower access and providing us the access in a speedy manner. Here is a list of references which is being used for the preparation of lecture. Hope you have enjoyed it. Thank you for a patient hearing. I will see you in the next lecture. Till then, take care. Goodbye.